Okay, we've just introduced the proper definition of continuity. We talked about it a little bit. Do you remember when we were doing limits? We had limit as f of x equals L, right? Limit as x goes to a of f of x equals L. Remember that we talked about how L does not have to be, it does not have to equal to f of a, right? When we talk about a limit, the value of f of a doesn't even have to be defined. So there's no reason this number L is going to be the same as f of a. But under certain special circumstances, they are equal to each other. The limit is the same as the value of the function. And in those special cases, that's what it means for the function to be continuous at a. I just wanted to say that again because it's so important. So let's keep going. So f continuous at x equals a means, let me just review quickly, what does it mean? It's easy. It's just the limit as x goes to a of f of x equals f of a. Now, this is the compact version of the definition, okay? I like it, but I kind of don't like it because when students first see it, they often miss a lot of the points that are hidden inside here. Like we talked about, for this to make any sense, both sides have to be finite numbers, right? In order for the left-hand side to be a finite number, the limit has to exist, and it has to exist as a finite value. Whereas on the right-hand side, to be a number, we need that a is in the domain of f, right? So f of a has to be defined. I want to rewrite this definition to make it a little bit more clear. So let's say it again. I'll just copy this. I'm going to say this definition again, but I'm going to be a little bit more precise this time. So what does it mean to be continuous at a? Well, first of all, f of a must be defined. Another way to say that is a is in the domain of f. That was in our informal definition, wasn't it? The second thing is that the limit as x goes to a of f of x must exist as a finite number. And thirdly, we need that these two finite numbers have to be equal to each other. I'm really saying the same thing as up here in the first version of the definition, but I'm just being a little bit more clear about the things that were hidden in the background. In other words, we need that function f of a be defined, or that value of the function of f at a be defined. We need the limit to be defined as a finite number. So notice how I say a finite number here, right? If the limit is infinity or minus infinity, there's no way it can be continuous there, okay? The limit has to be equal to a finite value. And thirdly, these two finite values have to be equal to each other. Limit is the same as the value of the function at a. That's special, right? That doesn't happen all the time for most functions. It does for polynomials, because polynomials are very nice. It does for other functions as well. But usually sometimes this is a special property, okay? Great. The next thing I want to do is even refine this definition or work it over a little bit more. Let me copy this again. The definition that I'm going to give right now, it's the same thing again, but the way I'm going to say it this time is actually the most useful version when you come to do problems, okay? So let's see how this this version of the definition would go? Well, the first thing that we need, this first part is going to be the same. F of A must be defined. But this next part is a little bit more interesting. Let's see what I write here. I'm going to say the right-hand limit is equal to the left-hand limit. As finite numbers, okay? So in other words, I can't have both sides being plus infinity or something. Each of these must exist, these limits must exist, and they have to be equal to each other. Maybe I should say that explicitly. These limits exist as finite numbers and are equal. So what do I mean there? That the right-hand limit exists as a finite number, the left-hand limit exists as a finite number, and those two values are the same. And thirdly, this f of a is the same number as the right-hand limit and the left-hand limit. F of a equals the value of the limit in part 2 above. How about I say that? So if both of these were 5, then f of a also has to equal to 5. Now, let's definitely do an example here to try to understand this definition and how we would use it, okay? So here we go. This is the kind of question I'm about to do right now is very common for a continuity problem. Often with continuity problems, you're going to be given a piecewise function, right? So why don't we say cx plus 2 if x is, I don't know, less than 1, and it's equal to 4 minus x squared if x is bigger than or equal to 1. What value of c will make f continuous at x equals 1? This is a very common kind of problem. And using this version of the continuity definition is going to be the most helpful, okay? First of all, the first thing, note, like, of course, in this question here, a is 1, right? And the first thing that we need is that f of 1 must be defined. Well, let's see here. When x is equal to 1, which of these two apply? It's the second one, right? 1 is greater than or equal to 1. So that means f of 1 is 4 minus 1 squared. And in other words, 3. So f of 1 is perfectly defined. It's equal to 3. So let's see here. F of 1 is defined. So that's a good start. Why don't we see what the next step would be to show that the left and the right and the left limits are the same, right? So let's do that. When I do the right-hand limit at 1, what happens? Well, notice that when x goes to 1 from the right, that means x is a number a little bit bigger than 1. For numbers that are bigger than 1, which option do I use? It's this one here, right? 4 minus x squared. So what I'm going to do is I'm going to recopy this limit sign, but f of x is going to be replaced by the formula that it is when x is a number bigger than 1. And that's true in this situation, right? Because x is going to 1 from the right, so x is a number a little bit bigger than 1. Now, how do I do this limit? Well, it's a polynomial, and the limit of any polynomial, whether it's a right or left limit, or two-sided limit, all I have to do is just put the number right in there, which, by the way, means continuity, right? But that's something different. Or like that's don't get confused on that. Right now, we're trying to decide on the continuity of this function f here, whereas what I was just stating right there is the continuity of this particular polynomial right here. Anyways, when we do the right-hand limit, we get 3, right? So let's think about the left-hand limit now and see what comes out for that one. When I go from the limit as x goes to 1 from the left, which formula do I use this time? Well, when x is going to 1 from the left, x is a little bit smaller than 1. So I'm going to use this first option, cx plus 2. So I replace the definition of f of x by cx plus 2. And cx plus 2 is a polynomial. It's a linear polynomial, degree 1. And I know that the limit of any polynomial, I can compute that limit just by substituting the number in for x. C times 1 is just c, so this is c plus 2. All right. Now, notice this equal sign here, right? Maybe I didn't say it, maybe I didn't emphasize it enough, but do you remember that when the two-sided limit exists, that means the right and the left limit are the same, right? That's why condition 2 up on this one is the same as condition 2 down here. So we have to guarantee that this right limit here is equal to this left limit. So in order for this condition 2 to be satisfied, we need that 3 is the same as c plus 2, right? And that tells me what c is, right? C is going to obviously be 1. So there we go. See, we now know what c is. I guess to be perfectly precise, we should check that f of 1 is equal to the value of up here. Well, notice when c is 1, this is 3, right? So these are both 3. So the last thing to check is f of 1 really equal to 3? Let's do that. We need to check that f of 1 is equal to the value of these limits here. In other words, 3. Well, let's see. What is f of 1? Which option do I use again for f of 1? I use the second one, right? Which is 4 minus 1 squared. Which is 4 minus 1, which is 3. And that's what I wanted, right? So we now have checked all 3 of these conditions. So our conclusion is, it's always nice to write a little quick sentence, I guess. F is continuous at x equals 1 only when c is equal to 1. So this is a very typical example. You can expect problems like this, and it's not too bad. We'll do some more, and then we'll get a little bit better feel for it.